is start with this decimal activity 2, card sort derivative match. In case you just join and for some reason you cannot get into this activity, I just sent the link again. Just click in there and let's go through it, right? Yeah, I will try to go as far as I can go so you guys will have a good background, a good reference for you to go through these activities. There's challenges, right? So let's let me enter. Continue without signing in. You can sign in your Desmos account if you have a Desmos account, or you can simply click here and type your name, right? Type your name. This time, I'm gonna join using Isaac Newton. Okay, yeah, great. Very good. So I'm entering as Isaac Newton, so you can see there the first challenge, right? Welcome, CG, welcome, Ruyung. I hope you guys are doing well. We are going over the Desmos activity 2. In case you need the link for this Desmos activity 2, here it is. Just click in there and you will be shown this, right? The first challenge is to pair up a function with its derivative. Pair up a function with its derivative, okay? So we have to do that here. But before we go there, I am going to show you here our Desmos graphing calculator, right? Here and here. And I'm gonna show you kind of the relationship, the main relationships between a function and its derivative, graphically speaking, okay? So for example, if you start here with this square function in its basic form, we all know that that function, when graph, shows this U-shaped curve called parabola, right? Parabola. Great. But now, what would be the graph of the derivative of this function? Well, we can graph the derivative, right? And by the way, what is the derivative of x squared? Anybody could tell us or could write it on the chat? Derivative of x squared? Twice x, right? Excellent. Twice x. So let's graph the function y equal twice x, the derivative, right? And I want you to catch this, guys. Notice the original function was this parabola. The derivative when graph is showing us a line, right? Somehow this function is simpler than this, right? Somehow when you take the derivative, you go from, let's call it a complicated function to a simpler function, right? So the parabola has as a derivative a linear function, right? Okay, great. Now, another thing I want you to notice is this. Look at this point, the special point, the parabola, the lowest point in this case, output-wise. This is called the vertex, right? The vertex. At the vertex, the tangent line is this horizontal line, right? Whose slope is 0. So at the vertex, the graph of the derivative should show 0, right? Should show 0. See? Yeah. Vertex, derivative, 0. Now, another thing I wanted to catch is this. When the parabola is increasing here from left to right, notice the graph of the derivative increases also, and it's positive, right? That's the relationship, right? Increasing here the derivative positive. Because remember, the derivative measures the rate of change. Going from left to right here, you are increasing, right? The rate of change is positive. So in the graph of the derivative, it should show a positive output, right? Okay. Now here, if you go from left to right, the values of the output are decreasing, right? Decreasing. So the rate of change is negative, as we saw yesterday. Remember when the ladder was falling, rate of change was negative, right? So the graph of the derivative should show a negative output, right? You follow, guys? Negative here on the left of the parabola with respect to the vertex, and on the right, positive. positive, right? Yeah, try to catch that. Now, this was with quadratic function is derivative. Let's do it now with linear function, and let's see what happens. Linear function y equal x. And let's see what is its derivative. What's the derivative of the linear function y equal x? Anybody? Or in the chat?
Y equal 1.
Y equal 1. Excellent. Excellent, Adriana. So y equal 1, right? Now notice the relationship. Look, if the original function is a linear function, such as this, y equal x, equal y equal to x, y equal to 4x, the derivative, simpler, look, a constant function, right? A constant function. I remember constant functions, they show a horizontal line when they are graphed, right? Because the output value never changes, right? So see, remember, from parabola, you get a straight line. From this oblique line, you get horizontal line, right? Try to remember that relationship to do the pairing here. Okay? All right, I think this is enough for this challenge. So we should be able to pair up. Let's close here. And this part will help us also in future lectures. Okay, so let's start pairing, right? Pairing. For example, I can pick a parabola and I could try to pair this up with some, I know that the derivative of a parabola, a quadratic function is a linear function. So let's say I pick this parabola. Which one do you think could be the graph of the derivative of this parabola? And hint, look at the vertex here of the original function. On the graph of the derivative, that should show 0, right? So at this point, it should show 0. If you don't see well, always you can click here and this becomes bigger, right? So at this input value 5, the graph should be 0, right? Should be 0. I'll try to figure that out. Yeah, so this goes with which line, right? There are several lines here, look, different lines. And try to remember also, right, that the vertex, the derivative is 0, but right after the vertex, the derivative is sort of positive. Before the vertex, derivative negative, right? Because the slope negative here, the slope positive here. So let's look for a match, right? For a match here. I want...
I think
the last one, Sarah, this one, or
I'm
yeah,
sure
but
no, it's on the left side.
Yes,
on the left side.
That one.
No,
this one.
No, the other one.
Yeah. Okay. Yeah. But let's think about it. Right? This one.
Yeah,
this
that's
one
what I
like
was
good,
thinking.
Yeah.
This will look like a good candidate. Very good. Excellent, guys. Yeah, because look, this one has at the vertex the input value 5, right? And we know that the slope of the tangent line, which is horizontal here, must be 0. So the derivative should be 0 at x equal 5. And this one is precisely saying that, right? X equal 5 is 0. And right after, derivative positive for this part. And before the vertex, derivative negative. So this looks like a great candidate. So let's pair this up, okay? Let's pair this up. When you pair, you just put it here and they will click. This looks good, right? Very good. Yeah, makes sense. Excellent. Let's choose another one, okay? And now, let me choose another parabola, but now one that is going downward, right? This downward. See, let's see if you can figure it out, guys. Let me this. Let's try to put it in the middle. Up here. This one. Any
the other
one. This one. Yeah, very good, Grace. Yeah. Yeah, Grace. Look, this at x equal -3 has the vertex. There, the derivative should be 0 because the tangent line is horizontal, right? Horizontal derivative 0 at x equal -5. This one at x equal -5 is precisely saying that, right? The derivative is 0 here at x equal -5. And right before, derivative positive, because from left to right, you are going up. The function is increasing from left to right, so good, makes sense. And right after the vertex, the output values are decreasing from left to right, right? So derivative negative. This seems to be a great candidate. Yeah, excellent, guys. Yeah, put it there and they will click. Yeah, good, right? Yeah, excellent. Yes, we have 2 cards. Yeah, now more. Now, more parabolas, right? I am choosing parabolas kind of because I know that the process of taking the derivative lesser somehow makes the new function to look simpler, right? So parabola should go with lines. So let's continue with parabolas. Let me get this one now. Let's see. This one, with which one do you think should go? What should be the derivative of this parabola open downward? And the hint, right? Look at the vertex. There's this, at this point, the derivative should show 0. It's -5 now.
Would it be the one on the left?
First left side.
The one on the left. This one. This one. Very good, Oscar. I think you got it, because look, this one is precisely 0 at -5, and to the right negative, consistent with the fact that if you walk along the parabola from left to right, this is decreasing, so negative derivative, negative rate of change. Here, if you walk from left to right, you are increasing, so positive. Excellent, I think is this. Yeah, make it click there. Yeah, we have 3 pair up, well pair up, right? Continue. Let's continue. I'm going to choose another parabola because I know that the process of taking the derivative, differentiation, will show lines, right? And then I will deal with the lines. All right, for this one, guys, which one do you think should be the one? Again, the trick is to look at the vertex. 2, I think. Yeah, which one do you think should be
on
here?
Right side.
On the right side, this one?
Yes.
This one? Let's see. Yeah, very good, Grace. Yeah, here, this is saying at x equal 2, the derivative should be 0, right? The vertex. So, this one precisely there is 0, right? At x equal 2. And moreover, after the vertex to the right, the function output-wise is decreasing, right? Decreasing, consistent with this fact that the derivative becomes negative. But before the vertex, the function is increasing from left to right, increasing, right? So makes sense because the rate of change positive. Excellent, this is this. I ran out of parabolas, right? I ran out of parabolas. So now I am going to deal with lines. But question for you guys, look, I have 2 oblique lines here, right? And I have 2 horizontal lines here. Which one do you think I should put on the top? An oblique line or a horizontal line?
Horizontal line.
But horizontal, but remember, yeah, oblique one. Yeah, very good, because the oblique will get, when differentiated, will give us a constant function. So it makes sense to start with this up here, right? And then once you take the derivative, a simpler function will appear here, something that will look like this, right? Very good, very good. But now which one? Let's say this on the left or this on the right. Which one is the derivative of this? Maybe we should make it bigger. For the derivative, let's use rise over the run. Rise 3 units, run 1 unit, 3 over 1, 3. So the slope should be 3. The derivative should be constant function 3. So which one do you think it is, this or this? This one, right? This one, very good, Grace. Very good, right? Perfect choice, because this is saying, if we take the derivative of this, the derivative captures the slope, which is 3, we will get a constant function y equal 3, this one, right? Excellent. And the last one, by the laws of logic, they have to be these 2, right? But let's explain, let's kind of verify, check that it makes sense. Okay, this is now a line that is decreasing. If you travel or walk along the line from left to right, look, it's decreasing. It's a decreasing line. Its a slope, therefore, should be negative, right? Negative slope. What is the negative slope? Well, rise is 2, run is 1, 2, 3, 4, or equivalently, rise 1, run 2, 1/2, but negative, right? Negative, because that from left to right, this line is decreasing output wise, right? Yeah, so negative 1/2 the slope. And this is consistent with this. Look here, this is showing at negative 1/2 a horizontal line, right? Very good. Excellent. So therefore, this is it. Yeah. Yeah, you follow, guys? Yeah, very good, very good. So we were able to do the pairing, right, nicely. So you may get a different order for the pairing. So they do what you have to do in your account and then show this, right? Show this, the first pairing. Okay, so let's go then to the next challenge, okay? Right. And again, guys, if you create an account in Desmos, it's free, it's OER material. Then whatever you do will stay there, right? And I will look at the last posting, the last time you posted your results, and that will be considered for your grade on the Desmos activities. All right, let's go to the next 6 challenges. Next question. It says, consider this function. Here is one of the cards from earlier, right? One of the cards that we pair up. As it turns out, it was one of the original functions, right? One of the given functions. Describe everything you know about its derivative. So what can we say about the derivative of this function here? Anybody would like to say anything, like any feature, anything that you can say?
You said the vertex is a -2.
-2. 2 actually, positive, right? Here.
+2, yes.
Yeah. So what happened at +2 derivative-wise? What's the derivative at 2?
It becomes -2. No, yeah, 1. It's 1, 2.
I agree, Sarah. At 2, something special happens. At x equal 2, if you go to the function and you take the derivative there, 0. Excellent. Yeah, Sarah, very good, very good. Excellent. At x equal 2, the derivative is 0. That's something that you can say, right? Yeah, so I could write at x equal 2, the derivative is 0. Yeah, and I want you to keep this in mind, guys, for the lectures that are coming next, right? Next week. This will be extremely important. Turns out wherever you see a crest, a peak like this, right? Then the derivative is always 0. So this crests, these mountains, they call it sometimes mathematicians mountains, should be associated in your mind with derivative 0, right? Yeah. Sometimes they call these points turning points, from increasing to decreasing, right? Turning point. Yeah, derivative 0. Excellent. Yeah, but what else can we say about this? Anyone could tell me what happens for x less than 2? What happens with the derivative? The derivative.
It goes to infinity?
Okay, for x less than 2, right? Advice, try to travel along the function. Are you increasing or decreasing from left to right? Increasing, right? Yeah, that's what matters. Don't worry about this being below the x-axis, above. Is the trend what matters. From left to right, if you walk along the curve, as you approach this 2, right, you are increasing. So for x less than 2, the derivative, therefore, since your output values are increasing, remember the derivative captures the rate of change, then the rate of change has to be positive, right? Derivative is positive. Yeah, it's another thing that I want you to kind of keep in mind. If a function is showing that the output values are increasing from left to right, it means that its derivative has to be positive, because the derivative precisely captures the rate of change, a positive rate of change. Okay, great, positive. And anybody could tell me what happens for x greater than 2? Derivative-wise, what happened with the derivative?
I think it's decreasing.
Decreasing. Yeah, the function is decreasing. So this means that the rate of change has to be negative, right? You follow, guys? Negative, right? Look, when it's increasing, derivative positive. When you reach the peak of the mountain, derivative 0. When it's decreasing, derivative negative. Derivative is negative. And we will see this formally later, but this kind of will help us to understand that, right? How the derivative controls the trend of a function, right? How we can tell you if your function is increasing or decreasing. Yeah, so I will write this. You can write this in your own words. You don't have to be technical, guys. I will take it as long as it makes sense. I will give you credit for it. And now what is important, as we explained right before, is to share with class. So click there when you go through this, and then you will see what I did, but also what other classmates did. Roberto Vélez. Roberto went through the challenges. The derivative will be aligned. It will cross the x-axis and the x equal 2. That's also so good, right? Okay, no? When you graph this derivative will be a positive here, and negative here will cross. Yeah, that's good. Yeah, and then after that will be negative. Very good explanation too. Or you can write something like this. It's up to you. All right, that was for this parabola, right? So now let's try to do more. This is easier, I think. It says challenge 3. Consider the derivative now, not the function, the derivative, right? We're gonna go backwards, the derivative. This is the derivative of some function. Here is one of the cards from earlier, the ones that we put in the bottom, right? The ones that we put in the bottom, the derivative, the graph of the derivative function. As it turns out, this was one of the derivatives. Describe everything you know about its original function. So any of you guys could tell me something about the original function whose derivative is this? And the idea is try to go backwards. Right? Remember, we showed that when we differentiate a parabola, as a result, we get an oblique line, right? And then I show, remember, when you take a line, an oblique line, and you take the derivative, you get a constant function, right? So what can we say about the original function of this? Should it be a parabola? Should it be a line?
It's a line.
It's a line. Adriana. Yeah, very good. Yeah, it's a line, right? It is a line. Describe everything you know about its original function. Original function is a line. The original function is a line. Function is an oblique line. Yeah, what was that, Sarah?
I wanted to ask, would it be correct if you said the slope is 0?
Yeah, the slope of this graph, but the problem is that if you are supposed to describe not this function, not this graph, the one whose derivative is this, right? And it's going to be like this, a function that is going to look like this, because you can see that the derivative here is 3, right? Positive derivative, right? The original function is an oblique line, right? And moreover, I can say that that oblique line has to have a slope 3. Why, Professor, why do you say that? Well, because 1, 2, 3 here, right? 9. With equation, for example, right? Equation y equal 3x, right? This function, when you take the derivative, will give you the constant function y equal 3, which is this, right? It's like a backward thinking. Yeah, this is something I could say, but other things could be said too, right? So say it in your own words. And now, important, share, right? Share. I see, look, Roberto, also Sarah also now, the slope 3, it is a line. Excellent, Sarah. I will give you credit for that, guys. Remember, these activities, it's not so much about being right or wrong, because some questions are open-ended questions. I just want you to go through all the activities, and I will give you credit for it. Yeah, very good, Sarah. Here, Roberto wrote original function must be have slope 3/1, consistent with a row, right? And then Sarah also supporting that. So very good, guys. Yeah, very excellent. Yeah, probably we can go over one more or two more challenges. Let's see what comes next. Yeah, another one here. says, how are two functions from another car sort? Here are two functions from another car sort. How are their derivatives similar? How are their derivatives different? Yeah. Could you point out something that is similar for the derivative of this parabola and the derivative of this parabola? Let's wait here. Try to think of something that derivative-wise is the same for this parabola and for this parabola. As a hint, look at the mountain here and look at the valley here. There's something there. And think of the derivative at those points, right? What would be the derivative at those points?
Wouldn't their derivatives both be linear equations? Or
Very good, Oscar. We're close. Yeah, Oscar is saying, right, the derivative of this, Oscar, this parabola will be this line, the tangent line, right? But the slope, what would be the slope of the tangent line here at this point?
Is it 0?
It's 0, right? Yeah, 0, right? Yeah, and then the tricky question is this, right? At this other parabola that is opening upward, right? What would be the tangent line at this point? Wouldn't be this horizontal line. So the derivative of this vertex, what would be?
0.
0. Very good, Sarah, right? So there we capture a similarity, right? Look, the derivative here at this valley and the derivative at this mountain, same, 0, right? 0. Right, so let's write similarity first, right? Similarity. You can write it any way you want, guys. Derivatives are at x equal, this is minus 1 minus 2, at x equal minus 2 for both graphs is equal to 0, right? Equal to 0, right? These are turning points, like remember turning points, right? From decreasing to increasing, this one from increasing to decreasing, turning points, valley, mountain, right? Derivative 0, I want you to make the connection in your mind there. For these extreme points, derivative 0. Yeah, that's one thing I could write, right? Now for number 2, in what sense these guys are different? So this is a little bit tricky, but let's see. Difference.
Because one from the left to the right becomes positive and one negative.
And the other? Yeah, very good, very good. Very good, Adrian is saying, right? The trends are different, right? Whereas this one is decreasing from left to right here, this one is increasing from left to right, right? And then this starts increasing from left to right, this starts decreasing from left to right, right? So the trends kind of are switched, right? The trends, yeah, the trends, difference, yeah, maybe we can write that. The trends are switched, right? When one is increasing, the other one is decreasing. When one is increasing, the other one is decreasing, right? You can write that whole thing in there too, but this probably will be good enough. Missing the I. All right, so, right, you see it, guys, right? Yeah, the trends are switched. Or someone could say also derivative negative here, derivative positive here, derivative negative here, derivative positive here. You can say also the sign of the derivatives are switched also, right? You can write it, the sign of the derivative are switch. Yeah, sign of the derivative between parentheses trends are switched. Yeah, That's it. All right, so share. Look. Roberto answers something to share function. That's very good. The difference of the trend opposite. Excellent. Great there. The derivatives will be similar in the sense that both of them will be lines. Yeah, also that's another similarity, right? The derivative of this is a line. The derivative of this is also another line, but as lines are kind of similar, yeah, that's good too. The difference because in the sense that one will be positive and the other will be negative as a good difference too, right? So feel free, guys, to find similarities and differences. These answers are not unique, right, for these challenges. So write something that makes sense, and I will give you credit for that, okay? All right, I think it's time to go back to a lecture. You just continue with the challenges. There are 2 more challenges left. So if needed, use the Desmos graphing calculator to figure out, given a function, how the parabola should look like, right? And then just go through the challenges. It should be fine. And if you have difficulty, just let me know. We can go over more challenges during the breaks or later, right? Okay, great, guys. Okay, so let's, any questions about the challenge, about this Desmos activity 2? Shall we go back to the lecture? Everything okay? Okay, let's go back to the lecture. And remember, you have time to do these 3 Desmos activities. The second one, the third one is coming up next week until August 17, okay? So as you get more knowledge, you can go back and refine your answers. That's the whole idea of these activities. Okay, so let's close this and let's go to our lecture today. Today, guys, we're gonna talk about linear approximations and differentials, okay? Let's start with this part, linear approximations, a very, very important idea that mathematicians figure out. And how does this work? Well, the basic idea is this. Often when you work with functions, when you graph your functions, you get some curve like this, right? Some curve. For example, if we take our function to be this function f of x equal square root of x, when you graph this function f of x equal square root of x, you get the half of the sideways parabola here, right? And if you want to confirm, you can always confirm. We have a tool here, our Desmos graphing calculator. Just put there this square root of x, and there it is, right? This is the graph of this function y equals square root of x. So in general, when you graph a function, you get a curve, right? And suppose you have this curve. But now, mathematicians ask themselves, right? We are very good at working with lines, right? It's easy to work with lines because the slope of a line is always the same, it's a constant, right? So they ask themselves, is it possible to approximate this curve with a line? That's why this section is called linear approximation, right? And the answer for that question was yes. But however, when you do this approximation, you have to be careful. And for that, I'm going to bring up an animation. It's available for you in our website. Is this the same curve, right? F of x equal square root of x. But I'm going to show you this idea, right, of approximating the curve with a line. First, you fix a base point. Suppose you fix your base point to be this, 4. And you want to approximate the curve with this tangent line. Notice if your base point is 4, if you are away from your base point, the tangent line and the curve, they separate farther and farther from each other, right? Farther and farther from each other. But notice that if you are in a very small neighborhood around your base point 4, the tangent line and the curve are basically indistinguishable, right? They're basically the same. So mathematicians said we could approximate the curve with this tangent line when we are close to the base point. Let's call it 4 for now. And this can be done on the right of the base point or also on the left of the base point. On the left, the same, right? If you are close to the base point, the approximation is good, but if you are far away, the approximation is not good. You see how these 2 points, they separate farther and farther from each other, right? So that's the whole idea of linearization, to approximate a curve with a line. What line? The tangent line. The tangent line. For this tangent line, to get the slope, we're gonna use the derivative, right? But this is the whole idea of linear approximation, right? In a small neighborhood of a base point, the tangent line and the curve are basically the same, right? Here, for example, basically the same. All right, we may go back to this animation, but let's do this with numbers now. Suppose you take as your base point the number 4, base point, okay? We're gonna use this as our base point, 4. This is called base point. Base point. The base point could be any real number, okay? So this, let's say we choose 4. The base point, in order to choose it, you kind of have to pick up a real number that is easy to evaluate with the function that you have chosen. Here I have a square root. The number 4 is a very good number for square roots, because if you take the square root of 4, that is exact, and that's equal to 2, right? Easy to evaluate, so 2, base point 4. But now, suppose we want to approximate the value of this f of 4.36. Let's say 4.36. It's close to 4.36 away from 4, right? So close to 4, close to this point. So then the approximation should make sense, right? Because notice that if you draw a tangent line here, as your base point there, tangent line, notice that the curve and the tangent line, since we are close to 4, are basically the same, right? There's a little gap there, but we can ignore that gap, right? So basically, if I'm trying to evaluate this guy, 4.36, at this function, square root of x, I can, instead of using the curve, I can use the tangent line, right? And then output this value, right? That's the whole idea, guys. And we're gonna do it formally. Now, at the base point, remember, at the base point, the evaluation should be easy to compute. It's just 2, right? Square root of 4 is just 2. But the challenge is to get this with a high level of accuracy, right? A good approximation. And for that, we're gonna use derivatives. So this guy, in reality, should be this, right? A square root of 4.36, but we're gonna approximate it using a linearization. Then he said, then we can use the equation of the tangent line, right? This guy at a equal 4, a is the base point 4, to approximate the value of this guy, right? A square root of 4.36. Okay, so that's the idea, right? And again, makes sense because you are close to 4. If you are away from 4, here, look, there's a huge gap. Wouldn't make sense, right? You have to be close to 4. Sometimes students ask me, how close, Professor? What do you consider to be close? For that, try to think about, try to think relatively speaking close, right? 0.36 compared to 4 is small, right? As a percentage of 4 is very small, probably 1%. 2%, right? In that sense, is close, okay? Yeah, and then remember, guys, we're doing this on the right. Most of the time we will do it on the right, but it can be done also on the left, right? You can choose points close to 4 from the left. All right, so here is the method that we're gonna follow to do this approximation. In general, right? In general, if you have any curve, not necessarily this one square root of x, right? Any curve, if you choose a base point A, and you go either to the right or to the left, a small amount, relatively speaking, right? Relatively speaking, then you're gonna get, let's say you allow yourself to go h units to the right. So you're gonna get a plus h on the right, h units to the left, a minus a here on the left, right? Now for a small h, between parentheses, relatively speaking, as a percentage, right? The tangent line should be approximately equal to the curve, right? To the curve. So this is the main idea. Linearization makes sense only if these two guys are close to each other. All right. Now, at x equal a, our base point, right? A. At x equal a, the slope will be given by this derivative of the function f of x evaluated at a, right? That's the slope of the tangent line. And the point will be this a comma f of a, right? A, its partner will be f of a via the function, right? Now, with a slope and with a point, we can figure out the equation of the line, right? The equation of this tangent line in general. So what will be that? Y minus y1 equal a slope multiplied by x minus x1, point slope form. From there, I can say that y minus y1 is this guy, y1, f of a, right? So y minus f of a should be equal to a slope. But what is the slope? We have it. Is f prime evaluated at a, right? F prime evaluated at a times x minus x1, but x1 is a, right? A, base point. So I get like an equation here. Now I'm gonna isolate my y, like we usually do, right? To figure out the equation of the tangent line, right? I'm gonna add to both sides of the equation f of a, okay? Here, this will cancel, y isolated here, and over here, I will get this. F of a, this guy, f of a, right? Plus the effect of the slope here, minus a, right? Yep. So this is the equation of the tangent line, right? The equation of the tangent line. Now, this is the equation of the tangent line at x equal a. This equation is called the linear approximation of f of x at x equal a. So we can approximate our function, our curve with this linear function, right? Easier to deal with, right? And mathematicians call this function the linearization. So this is called the linearization of the function at the base point a, okay? At the base point a. This is this, right? And then they symbolize this with an L, with a capital L, L of x. L stands for linear, right? Linearization. So the linearization of the function is this formula. F of a plus f prime of a times x minus a, where a is the base point. Okay, so now the big fact is this, right? As I show you in the animation, for input values x very close, relatively speaking, again, we can write here, right? Relatively speaking. To a, the base point from the left or from the right, f of x is approximately equal to this linearization, right? That's the big deal, guys. Because if you can work with a linear function instead of a crazy function that they give you, at least locally, it's good, because working with a linear function is much easier than working with a function in general, right? So this is a good idea. And actually, this is the algorithm that your calculators, including Desmos scientific calculator, use to output values, right? It's just that they use a high level of approximation, and you don't notice that the output values that you get when you take square roots or when you try to figure out output values of complicated functions are done inside the calculator. In the coding, they use this linear approximation, right? Yeah, they do. A very nice idea. Okay, so first, let's try to secure this. Let's try to see if giving a function, we can easily figure out its linearization, right? Its linearization. And then we will do some approximations. I will show you. So let's see here, for instance, example 1. Suppose you have this parabola f of x equal 3x squared plus 4. And they say, find the linearization L of x of your quadratic function, right? At the base point a equal 2. The base point a equal 2. So let's do it together. So you start by writing out your linearization formula. Linearization formula is equal to this: f of a plus f prime of a multiplying x minus a, where a is the base point. Now, I know that a is 2, right? It's given here. They want me to take the base point x equal 2. So my linearization then should be equal to what? F of a, which is 2, plus the derivative of my function evaluated at 2 times x minus 2, right? I have replaced a with 2. Very good. Now I have to get this evaluation f of 2, and I have to get this other evaluation f prime at 2, right? 2 evaluations that I need there. So for that, I'm going to write on the side this: f evaluated at 2 is just the evaluation of this function f of x at x equal 2, right? So we use the function. So f of 2 will be equal to what? 2 squared, 4 times 3, 12. 12 plus 4, 16, right? 16. If the numbers are not so friendly, you can put this in your calculator, right? And you should get 16 there. Great. Now, they want evaluation of the derivative. Let's find the derivative first. What is the derivative of this? Anybody could tell us what's the derivative of this function?
6x.
6x. Excellent, excellent, right? Derivative of this, 6x. 6x. Excellent, excellent, guys, right? 6x. Now, we have to evaluate this derivative at our base point 2. Well, it's just about substituting x with 2. 6 times 2 will be just 12, right? 12. So you will do these computations on the side, on the calculator, right? Great. Now that I have the ingredients for my recipe here, look, I just substitute them. L of x will be equal to what? F of 2. F of 2 is 16 plus the derivative evaluated at 2. The derivative evaluated at 2 is 12. 12 times x minus 2, right? This should be the linearization. Now, remember, mathematicians, they like to see results simplify, right? Simplify. As I explained, guys, if you are working on your homework, if you put this as your answer, linearization, the computer will take it. But when you work on worksheets or when you work on your exams, in order to be able to identify the answer, you have to simplify, right? Simplify. So we're going to do that next. So simplifying this, we'll get this 12 times x, 12x minus 12 times 2, 24, right? 24. Now combine like terms, 16 and 24 like terms. 16 minus 24 is just -8, right? negative 8. I am going to write first 12x and then negative 8 here. Right? Kind of to follow the what they call a slope intercept form, right? For the equation of a line. So this is it. Very good. 12x minus 8. And this is what mathematicians call the linearization, right? This is called the linearization of f of x at a equal to. Very important, the base point, guys. The base point to determines this linearization, right? If you change your base point to 3, a different linearization will come up, right? Yeah. So the base point is important. So let me bring up again the animation. Look, the base point is this, right? If you change it, let's say we said 4 in the example, right? This is the linearization. But if you change the base point, let's say to 6, the tangent line changes, right? So the linearization changes according to the base point, right? According to the base point. All right, great. So now I have something similar that I just did here, but in your worksheet on your own, try to get the linear approximation or the linearization for this function. I will write the formula for you, okay? I will write the formula for you. The linearization L of x is equal to this. F of A plus F prime of A times x minus A. Try to write this down somewhere. This is the formula for the linearization, where A is the base point, right? And they give you the base point is this guy, A equal 1, right? 1. So 1 should go here, here, and here. Try, give it a shot, and let us know if you get the answer, okay? So L of x, F evaluate at 1. You have the function to the evaluation there, plus the derivative of the polynomial function evaluated at 1 times x minus 1. Very good. Yeah, compute this guy, then compute this guy with a derivative, and then just simplify, and it should appear there, your answer. Aha, I see. Some students are posting answer, which is good. Oscar, Adriana. Excellent, guys. Yeah, you made my day. Very good, very good. Excellent. That's what it is, right? That's the linear approximation. And then again, guys, if you think about it, right? These linearizations give us a way to deal with complicated functions using linear functions. It's an important idea. All right, great. So let's do it together, right? On the side, I'm going to do some computations here. F of 1, what is that? Well, it's what I get if I replace x with 1 here. Plus 1. This is 1 times 2, 2, minus 2, 0, 0 plus 1, 1, right? Or if the numbers are not friendly, use your calculator, you will get 1. Derivative of this polynomial function is just 2 coming down, multiplying to 4x, 1 less on the top, minus derivative of 2x, 2, right? 2. But I want this derivative at 1, evaluated at 1, right? So let's do that. So this will be 4 times 1 minus 2. 4 times 1 is 4, minus 2 is just 2. So this one is 1, this is 2. And then you just simplify, right? Simplify in order to get your answer. This is going to be equal to 1 plus 2x minus 2. 1 minus 2 is -1. So the linearization should be equal to twice x, this guy, 1 minus 2 minus 1, right? Excellent, excellent. And this is what this is showing. Excellent. Now, we have to do linearization with these square root functions. So let me give you an example, okay? Let's go back to lecture, and then we will go back to that question on the worksheet. Example 2, suppose we have this square root function, and they ask us to find the linearization of this function at base point a equal 4, just like in the first example, right? And then they say, once you get the linearization, use that linearization to estimate this square root of 4.36. So let's do that together. So first, I'm going to compute the linearization L of x, which is basically just the equation of the tangent line, right? L of x will be f of a plus f prime of a times x minus a, right? That's the linearization. So basically, I need f of a, but a, they say, is 4. They're telling me that the base point is 4. Then the derivative evaluated at 4, x minus 4, right? I need these guys, f of 4, f prime of 4. So on the side, I am going to compute them. First, f evaluated at 4. F evaluated at 4, when we look at this function, f of x equals square root of x, has to be just a square root of 4, right? Substitute x with 4. But this is just 2, right? So this one done, 2. Derivative of my square root function. Remember, we have that, right? The derivative of the square root function in simplified form is this, right? 1 over twice square root of x. If you have not memorized this formula, guys, which is very useful, write it down somewhere, have it handy, okay? Now, I want the evaluation of this derivative at my base point 4. So we are talking about 1 over twice the square root of 4, right? 4. So what is that? Well, you can put this whole thing in your calculator, or just realize that the square root of 4 is 2. 2 times 2 is 4, is 1 over 4, right? Or a quarter, 1 over 4. All right, so time to substitute our values here. So the linearization will be equal to f of 4 is just 2 plus the derivative of the function evaluated at 4 is 1/4. That must multiply x minus 4. So let's do the math and simplify this here. This will be twice, or 2, 1/4 of x minus 1/4 of 4. But 1/4 of 4 is just 1, right? It's just 1. So finally, our linearization will come down to this 2 plus 1/4 of x minus 1. But 2 minus 1 is just 1. So bottom line, the linearization of this function is this: 1/4 of x, or 1/4 times x plus 1, right? This is the linearization. This answers part A, right? They said find the linearization, right? At the base point a equal 4. Part B says use that linearization to estimate this. So remember, we said that if you want to evaluate a function, a complicated function, instead of plugging this into the function, you can use its linearization, right? Its linearization. So the square root of this 4.36 will be approximately equal to 1/4 of x. Here is 4.36, right? Plus 1. radical function versus linear function. This is easier to deal with, right? So that's the whole idea. So in your calculator, you compute this, okay? So a quarter of 4.36. Parenthesis here, 4.36. And then plus 1. 11.9, 11.9, right? I unnecessarily put a dot there. 1/4 of 4.36 plus 1, 2.09. This is it, 2.09. Okay, 2.09. And now, guys, I want you to notice the following. I'm gonna write here, notice that the square root of 4.36 computed exactly, right, using our calculator is the following. I want you to notice this is very important. 4.36 is this point. This is in reality what the output value for input value 4.36 is using the function itself, right? Square root of 4.36 is this, 2.08806. 2.08806. Now, what is important is I want you guys to compare these two. Compare these two. 2.09, 2.08806. These two guys are very close to each other, right? This is a very good estimation of this, right? That's the whole idea of this process, of this linearization. It gives you a very, very good estimation of the actual value. So these two guys, very close, very close. So it is a good approximation, right? Very good, guys. This is it. Now, I want you to understand this, guys, because of this. Sometimes when on the exercises, on the worksheets or on the homework, they say approximate the value, the square root of some number using linearization. This is the number that they're expecting you to pose as your answer, not this, right? They're close to each other, but different, right? So this is the one that they want always when they say use linearization, right? To approximate this guy. All right. But it's always good to check in the end, right? And make sure that they're close to each other, right? The approximation with the actual value, because if not, it means that you did something wrong, right? They have to be very, very close to each other. Different, but very close to each other. All right, so this is the way we're going to deal with radical functions, right? So now, please try this one. And then I will show you how to do it with cube roots, function that involves cube roots. So can you try this now, guys? Do this, right? F of x equal a square root of 4x plus 49. And the base point is 0. It's an easy base point to work with. I'm going to give you as a hint that the linearization has this formula. Is the function evaluated at the base point first, plus the contribution of the derivative here. Look, f prime evaluated at a times x minus a. So try to figure out the linearization there. You may have to use the chain rule for the derivative of this composite function, right? Radical function outside function. This guy inside function, right? And the derivative of the square root function, I will right here recall. The derivative of the square root function is just in simplified form 1 over twice the square root of x, right? Yeah, very good. You use that together with a chain rule, figure out the linearization there. I see. The students have worked on this, which is good. Adriana, Oscar, you guys made my day. Very good, very good. Yeah, that's what it is, right? That's what it is. Yeah, it's a little bit long, but it's just derivatives again, right? Derivatives. Yeah, and this linearization process, guys, if your career has to do with computer science, it's very important because this is actually the algorithm that calculators, computers, they use to compute locally output values. It's just that they do it with a very, very high level of accuracy. Yeah, the derivatives, they turn out to be very, very useful, a very, very useful tool. All right. So let's do this together, okay? So we can move on and consider more different cases. All right, so I have to compute the linearization, right? So on the side, I have to get this guy and this guy, right? Which are the following: just f evaluated at 0 plus the derivative of f evaluated at 0 multiplying x minus 0. 0 is nice. Look, it will disappear from here, right? So it will save as work. All right. So, but let's figure out what is f of 0. F of 0. F of 0, looking at our function, is just this. A square root of 4 times 0, right? I'm substituting x with 0, plus 49. So what is this? F of 0 will be, this disappears, 4 times 0, 0, a square root of 49. But the square root of 49 is exact, is 7, right? It's 7. In case you forgot it, get it with a calculator. Don't get it stuck, it's just 7. Great. Now, the derivative. First, let's figure out the derivative of this composite function. We start with the derivative of the outside function, which is given by this formula, 1 over twice the square root of something. That something in general is this 4x plus 9 times the derivative of the inside function. But the derivative of this inside function, easy to compute. Derivative of 4x is just 4. Derivative of this 0, so it's just 4, right? 4 times 4. Now, I want this not in general, but evaluated at 0. So let's take advantage of that. Look, 4 times 1 is 4. There's a 2 here. 4 times 0 plus 9. 4 times 0, 0. I'm left with this guy. 2 into 4, 2 divided by square root of 9, right? But this is just 2 over 3 because the square root of 9 is just 3, right? 3. Yeah, so this is 49. Sorry, this is 49. We forgot a 4 there.
I was just about to ask you that,
yeah.
Professor. You had me all confused.
Yeah, this was 49. Sorry, this was 49, right? Yeah, very good. So this will be 7, right? Excellent. Very good that you're following, guys. Yeah, it's just that sometimes the numbers are all over the place. So square root of 49 is 7, right? Now everything clear? Nice? Yeah, great. Excellent. So now time to substitute our values, right? Time to substitute our values. So f of 0 in the linearization should be just this guy, 7, right? Plus the derivative evaluated at 0. We agree 2 over 7. And this 0 disappears. So this will be x, right? So the answer sort of came out itself, right? 7 plus 2, 7 times x, which tells us that just this, right? Yeah. Very good, guys. Now, they are asking here to figure out the linearization of this cube root function. Let me show you how to do that, right? Not a square root, cube root. So let me show you an example and then we'll go back to that, okay? So, and there are also trigonometric functions. So since we are here, probably I can show you how to deal with trigonometric function, and then I will show you an example for the cubic root function. Let's say they ask you to find the linearization of this function, f of x equal tangent of x, right? I'm gonna do this and then you will do number 5, okay? Tangent of x at this base point a equal pi. How we proceed? Well, the linearization has a formula, right? The linearization of a function is equal to f of a plus f prime of a, the derivative, times x minus a, right? So we need this, f evaluated at pi plus the derivative of the tangent function evaluated at pi times x minus pi, right? We need this guy, we need this guy. Let's compute them on the side. What is f of pi? According to this formula, f of x equal tangent of x, f of pi should be tangent of pi, right? But what is tangent of pi? Anyone could tell me? You can check on your calculator.
It's 0.
0, right? 0, yeah, because it's sine over cosine, sine of pi is 0. Okay, now when you use the calculator, be careful, guys. This gives you by default the computation in degrees. But go to radians, 0, right? 0. 0 is what we're gonna write then. Excellent, excellent. 0, right? So this one done, 0. Now the derivative. Anyone could tell me what is the derivative of tangent of x? Do you remember, guys?
Is it gonna be sec squared?
Secant square. Very good, Sarah. Secant square, right? Secant square of x. In case you forgot, I have sheets, right? Where the derivatives are shown. I think it's here. Let me see. I think it's not this one. Yeah, this is the inverse functions. This is it. Derivative of tangent secant square, right? Yeah, in case you forget, it's there. Try to print these sheets out and have them handy when you do your work. Very good, secant square, right? Okay, so now, but we want this evaluation, f prime at pi, right? So we're gonna evaluate secant square of pi. But remember, in the calculator, there is no secant, right? There is sine, cosine, and tangent. So I'm gonna rewrite this secant square as 1 over cosine square of pi. Follow, guys? Because remember, secant is 1 over cosine. A square in that, 1 square is 1 over cosine square of pi. So let's compute this, right? What is this guy? Well, cosine of pi is -1, so it should be 1, the whole thing. But let's confirm, right, this in the calculator. 1 over cosine of pi. But remember, this must be squared. So this whole thing squared. And remember, you must compute this in radians, not in degrees, but in radians. Be careful there, guys, right? 1 in radians, right? This is 1, right? So this guy 1. So we have that. So let's replace everything. L of x will be f of pi, which is 0, plus f prime of pi, derivative of that by 1, times x minus pi, right? And this simplifies to the following. 0 disappears. 1 times any quantity is just the same quantity, right? That's it. So believe it or not, guys, the answer for this number 4 is just this guy. Following this strategy, can you try number 5? Instead of tangent function, now it's sine function, right? It's possible to figure out linearization for sine function too. And the base point now is easier, is 0, right? So maybe I should write out the formula for the linearization, right? Try guys. L of x equal f of a plus f prime of a times x minus a. This is the linearization. And since our base point is 0, you're supposed to put 0 there, right? Yeah, work on this. Yeah. 0 is a friendly number, right? So no hard to deal with it. I see. Oscar. Great, excellent. Yeah, very good. Yeah, very surprising the result. But it is what it is, right? You follow the rule, guys, whatever you get. If you follow the rules, the steps, that's what it is. Sarah, very good, excellent. Very good. So let's try to do it together. We need f of 0, we need f prime of 0. We are going to get them here on the side. F of 0 first. What is that? The function I'm dealing with now is this, sine of x, right? Sine of x. So this guy should be sine of 0. But what is sine of 0? Anybody could tell me what is sine of 0? Yeah, CG, very good. Sine of 0, guys, if you look at the 0, excellent, right? Excellent, because the unit circle has for 0, the coordinate 1,0, the second coordinate is sine, so 0, right? Or if you put it in the calculator in radians, it will give you 0. Excellent. Now let's take the derivative. Derivative of this function should be derivative of sine. Anybody could tell me what's the derivative of sine?
Cosine.
Cosine, excellent, right? Cosine. Very good, cosine of x, right? Now, the derivative evaluated at 0. Anybody could tell me what is cosine of 0?
1.
1, right? Excellent, she 1, right? Yeah, it's a surprising result sometimes for some students, right? Sine of 0 is 0, but cosine of 0, 1. Why, Professor? Because on the unit circle, the first coordinate cosine 1, the second coordinate sine, right? That's why. Or you can get it in the calculator, but make sure you are working in radians, right? In radians, not in degrees, in radians. Okay, done with this. So let's put our stuff in here and get the linearization for the sine function. F of 0 turned out to be 0 plus the derivative of the function sine at 0. Cosine of 0 turned out to be 1 times x minus 0. This 0 disappears, right? This 0 is nice, disappears from the scene. 1 is also another nice number when you multiply, disappears too, right? 1 times x is x. So L of x, linearization of the sine function, believe it or not, guys, is the identity function. The linearization of the sine function is the identity function, right? At base point 0. Wow, Professor, identity function, the linearization of sine. Can you show us some evidence of that? Well, guys, if you have y equals sine of x, right? This is the graph, right? Now, we are saying that the linearization of this at base point 0 at this point is a line. And what line? Y equal x, right? Look, make perfect sense. If you see there, look how close is the tangent line to the sine function around the input value 0. Makes perfect sense, right? To approximate the sine function with this line when you are in a close neighborhood of 0, right? Yeah, all these guys, I encourage you to explore, right? When you have a fact and kind of doesn't make sense, graph them and try to see that indeed this guy is a good approximation for this, right? Yeah, play around with this Desmos graphing calculator. All right, great. So we did this. Now I have to show you how to deal with a cubic function, this, right? Yeah, this is gonna be a little bit tedious, but doable as usual. So I'm gonna show you here, this over here. We did the square root there. I guess at the end here. Yeah, here. Yeah, and then we will do differentials in the end. Example 3, I have it as example 3. Find the linear approximation of the function cube root of x at a equal 8 base point, and then use it to approximate cube root of 8.1, okay, to 5 decimal places. They want 5 decimal places, okay? All right, let's do it together. So let's just write this nicer. Okay, so solution. We have to start by figuring out what is the linearization of the cube root function, right? The linearization. Once we have the linearization, we will use it to do the evaluation at this input value 8.1. All right, so the linearization, remember guys, has a formula. What formula, professor? Is this formula, f of a plus the contribution of the derivative. Derivative evaluated at a times x minus a. Now, the base point is 8, right? So our linearization will be equal to f evaluated at 8 plus the derivative evaluated at 8 multiplied by x minus 8, right? I have substituted 8, the base point, with 8. And now we gotta compute this guy, we gotta compute this guy, right? And that we're gonna do it on the side here. So what would be f evaluated at a if we are working with this cube root function? Well, it will be the cube root of 8, right? But the cube root of 8 is just 2, right? 2. Sometimes students ask me, professor, how can I take cube roots in general here in the Desmos scientific calculator? Well, if you choose this, Desmos scientific calculator will give you a chance to input the index, to post the index there, cubic root, right? Cubic root of 8. And it's a reasonable request because sometimes this number might not be 8, might be 27, might be some big number, right? Use this. Cube root of 8, 2. Great. Now, the derivative. For the derivative, we have to do this. Derivative of this function is going to be equal to what? Well, notice that the function itself first is cube root of x, right? I can write it as x raised to 1/3, right? Remember, when you have radicals, the denominator is the index. So x raised to 1/3 is cube root of x, right? Now in this form, the derivative should be easier to take. Derivative will be equal to what? Exponent comes down up front, 1/3. What stays? 1 less, right? 1 less. 1/3 minus 1. Continue here. Derivative, 1/3 of this subtraction, 1/3 minus 1. If you place 1 here below, 1/1 is 1, and you take the LCD 3, this tells you that you're going to multiply both numerator and denominator by 3. You end up with this 1 minus 3 on the top, which is minus 2, and 3 on the bottom, right? The LCD. So this is the derivative. 1/3 x raised to negative 2/3. Now, let's just write our derivative nicely so we can keep it as a final result So whenever you deal with cube roots, you don't have to take the derivative again. Look, mathematicians don't like negative exponents as part of final answers, right? So what they do is they rewrite this power with negative exponent as this: 1 over x raised to 2 over 3. Another thing that mathematicians don't like is to see fractional exponents. They don't like that. So instead of x raised to 2/3, what they write is this: 3. Okay, 1 more times 1 is 1. 3 here. Look, x raised to 2/3, they write it as this: cube root of x squared. This is this, right? I don't want anybody to get lost. The denominator is the index, and the numerator is what you write here, okay? These guys you should have perhaps on your notes, just like we got the result for the derivative of the square root of x as 1 over 2 square root of x. This is the derivative of cube root of x, 1 over 3 times cube root of x squared. Now, with that result, then it's easy to compute this f prime at 8, right? Why you say that, Professor? Well, because look, if we put this in here, 8 squared, right? 8 squared is 64. Cube root of 64 is 4. 4 times 3, 12. So 1 over 12. Mm-hmm. And this guy, 1 over 12, can be gotten also with the calculator, okay? How, Professor, can we get it with the calculator? Well, check this out: 1 over 3 times cube root, right? Cube root, so you click in here, cube root of x squared. We said x is 8, right? 8 squared. Aha, Professor, I got the decimal representation. Click here, 1 over 12, right? The fractional representation. So that's what we got there. All right, guys, use your tools, don't get stuck. Okay, so let's replace everything, right? Here then. The linearization then should be equal to this guy, right? Which is cube root of 8(2) plus this guy we found out that is 1 over 12 times x minus 8, right? This is the linearization. Now I can simplify and then present my answer in a slope-intercept form. That is in case they want you to find the linearization. But notice, guys, that in this case, they just want you to approximate this, right? To approximate this. So then what I'm gonna do is I'm gonna just put this directly there on the linearization formula, this guy, okay? This guy in blue, I'm gonna just put it there because this is the formula, right? And then I will compute it in the calculator, right? Now, let x be equal to 8.1, right? What they were asking you to approximate. So we do that, then our linearization should be 2 plus 1 over 12, 8.1 minus 8. And this is approximately equal the value of cube root of 8.1, right? Approximately equal. Put this in your calculator. Notice that this difference is 0.1. So this whole thing in the calculator then should give us the final answer, the approximation via our linearization, right? Yeah, so we go ahead and do 2 plus 1 over 12 times 8.1 minus 8, right? 2.00833. They wanted us to approximate this to 5 decimal places, right? 1, 2, 3, 4, 5. So we're gonna write this whole thing right up to here. Very good. So let's write it down. 2.00833, right? Rounded to 5 decimal places following the instructions here, 5 decimal places. Now, guys, advice, once you are done with this approximation, calculate the actual value and make sure that this approximation is really close to it. Look, if you calculate the actual value, right? Cube root of 8.1. This guy is very close to this, right? Look, up to the third decimal, they are the same. So good, right? So makes sense, right? So they want this. They don't want this when they ask you to approximate, right? So be careful there. Very good. All right, so we're gonna take this as the derivative for the cube root function, right? 1/3 cube root of x squared, right? And using that, then we can go back now to our worksheet and work on that. Okay, so see this. And then we will deal with differentials. Yeah. Can you try? It's here somewhere. I saw it. Yeah, this. They want the linear linearization of this function, right? So let's do that. Yeah, f of x is equal to cube root of x. Find L of x equal f of a plus f prime of a times x minus a. They want this to be done at a equal 27, right? So you gotta try this. And I'm gonna give you the result for the derivative of the cube root function. Derivative of cube root of x with respect to x is just equal to 1/3 cube root of x squared. Yeah, use that, guys. This for this part. Go ahead and try, guys. Yeah. And in this case, I think you have to simplify because they're asking you for the linearization, right? The linearization. And for the addition of a fraction, try to use the calculator too. That may help. Let's check. Very good, very good. Very good, very good, Adriana. Very good. Great, great, awesome. Yeah, you got it. Yeah, and try to recall these guys for your homework because these cube root functions, they will appear in some questions on your homework. So try to remember this part. Okay, guys. More students are posting. Oscar, very good. Very good, Oscar. You got it too. Yeah, let's do it together, right? Excellent. So the function evaluated at 27, not a problem because it's just cube root of 27, right? And this is just the number 3, right? If you don't remember that, use the calculator, it will give you 3, right? Cube root of 27. Now, the derivative of the function, is what? We said that we're gonna use this result, right? That we just showed, right? The derivative of this cubic function is this, 1 over 3 times cube root of x squared, okay? Now I want an evaluation on this function, evaluation at 27. So I have to get 1 over 3 times the cube root of 27 is squared, right? The square. A crazy number, right? So we can use our calculator and let's just do that. Cube root of 27 is 3 squared, 9 3 27. 1 over 27 should be this. But again, guys, in case you cannot do this in your mind, just simply use the calculator, but properly, right? So 3 times cube root. For cube root this, you have to place there the index of the radical, right? And then 27 is squared. Desmos calculator gives you by default the decimal version, but clicking here, you get the fractional version, right? So 1 over 27. So this is it. 1 over 27. So now this is what goes there, right? The rest should be just simplification. So let's do this, and I will show you how you can get this with the help of your calculator if needed. This derivative is, we just show is 1 over 27 times x minus 27. Now let's distribute our multiplication over. Here, the linearization will be 3 plus 1 over 27 times x, 1 times x, x. This one, let's see how they have written it. Yeah, they have written it this way. 1 over 27, right, times x. And 1 over 27 times 27, 27 into 27 is just 1, right? 1. 3 minus 1 is 2. So L of x is 1 over 27 x plus 2. And that is here, right? Excellent, excellent. This is this guy, 1 over 27 x plus 2. Excellent, excellent. Very good, guys. Very good. Okay, I think we are ready for the second break, and then we will deal with these computations directly. I will show you a trick shortcut, okay? And then we'll have to talk about differentials. So that's the last part, okay? Similar. I'm gonna do the first one and show you how this can be done somehow quickly. Suppose they ask you to use linear approximations to calculate this, a square root of 64.25. How can we do this directly, sort of in one step? Well, you know that this computation can be done using the linearization, right? So one thing you can do is this, directly you write this, the square root of 64.25 will be equal to what? Well, first, I want you to select your base point. The base point, for the base point, choose again some real number such as 64 here, whose square root is easy to compute. So let a v equal to 64. The base point has to be close to this guy, and 64 is close to 64.25, right? So it makes sense to take, okay? Now, let the function be equal to a square root of x function, right? Again, base point 64, function square root of x. And with these two, directly do this. F evaluated at a plus f prime evaluated at a times x minus a, okay? Now, this, since our base point, we cleverly chose to be 64, will be the evaluation of 64 plus derivative evaluated at 64 times, what do you write here? This we know is the base point 64, right? But what should be x? X will be this. So directly put x as 64, right? 64.25 there. This is gonna help you. Okay, now let's get it done, right? What is this? This is just the square root of 64, right? The square root of 64, but that's 8, right? That is 8. Square root of 64, 8. Done. What is this? Remember, the square root of this function is 1 over twice the square root of x, but just put the 64 there. This will be 1 over the square root of 64 is 8, 8 times 2, 16, right? Or you can calculate this in your calculator. And this difference, guys, is just the 0.25, right? The 0.25. You see?
That's right.
Yeah, right? Okay, guys. So, a square root of 64, 8. 8 times 2, 16, right? We multiply, we consider the 2 there. Great. And then that's it. This is your answer. This is what you have to come up with. So take your calculator and then just do this. So this is sort of a direct way to deal with these approximations using linearization, right? So it's a kind of a quick way, 0.25. And that's it. It's giving me 8.015625. Follow the instructions for the rounding. They say round to 5 decimal places, right? So you're gonna go up to here, right? 5 decimal places. This number 2 becomes 3, right? Becomes 3. So it's this guy, right? The first one, A. Follow, guys? Yeah, great. So for number 6, we're talking about A, right? A. Rounded to 5 decimal places, they should be this. So 8.01563, right? Rounded to 5 decimal places. You see? It's like a little shortcut, but again, the important thing is to choose the right base and the right function, right? Great. Now, can you try this using the shortcut, and then we will do the cube root probably quickly in the same way. Try this, guys. This is very common in the exam. So just to approximate, they're not going to give you the function, but the hint is, right? Let base point be a real number close to this. Could be on the right, could be on the left. Sometimes it's on the left. It's a little bit tricky, but I hope here we are getting this 16, right? Yeah. Base point 16, and let your function be the square root function, right? And directly say, okay, this will be equal to the function evaluated at the base point 16, not derivative, without derivative first, plus the derivative evaluated at 16 times x minus a, right? But x minus a is 16 minus 16 point x, this guy, right? 16 point this guy. 16.3 minus 16, which is going to be a small number, right? And that's it. That's all we're going to do. And estimate that using the linearization. Yeah, we are talking about the square root here, right? This one over twice the square root, right? I see students figure this out, right? And try to follow this because it's like a shortcut. Two students figure this out. Number 7. Very good, Adriana. Very good, Ruby. Very good, right? Yeah, so evaluation of the function is 4. And this you can put directly in the calculator, but I'm going to just do 1 over a square root of 16 is 4. 4 times 2 is 8, right? And I will put this in the calculator. This difference, notice, is just 0.3, right? 0.3. So. Or you can put that in the calculator in case you forgot. All right, so this all computed gives me the following, right? Approximately equal to, together 4 plus 1/8 times 0.3. 4.0375, right? It is rounded to 4 decimal places, right? 4.0375. Notice how the numbers are close to each other, guys. Very good, very good. This is 4.0375, following the instructions for the rounding, right? So very good. Excellent, excellent. I think someone else, Sarah, you figured it out too. Excellent, excellent. Very good, very good. This one with cube root. Let me show you with a shortcut what to do quickly so you can do it in your homework. They want you to estimate this, right? Cube root of 1.006 using linearization. All right, we know first thing, evaluation of the function, right? Evaluation of the function. But even before, you're supposed to choose the base A, B, what? For the base, choose a number that's easy square root and is very close to this guy from the left or from the right. Sometimes you might have to choose a number from the left. The A1 here, reasonable. Then f of x, work with cube root now, right? Cube root, not the square root, cube root. So the linearization says the evaluation at the base point 1 first, plus the contribution of the derivative. Derivative evaluated at 1 times x, right? But that x is this guy. That x is this guy, right? We said it's this guy, this guy. So that x is just this guy. Let's put it directly there. So, this guy, the whole thing here. 1.006 minus the base point, right? The base point 1. All right, so this is the cube root of 1, easy to compute, just 1. Derivative, remember we said derivative of the cube root function is 1/3 cube root of something squared. That something has to be the base point 1, right? This is the derivative times this difference. This difference is just 0.006, right? Yeah, and then just compute this in the calculator. This is 1/3, right? This is also 1. You can put all that in the calculator, or you can just do it this way. But what is important is that you should end up with the following: 1 plus 1/3 of 0.006. Yeah, 1/3. Erase characters that are not needed. This is it, 1.002, right? 1.002. So let's see which one is this. Is there, right? Or 8. Very good, guys, very good. Is this D? 0.002. Excellent. All right, follow the shortcut, it'll help you. Now, to finish, guys, let's talk about differentials, right? So go back to lecture and let me explain this topic called differentials. It's another tool that engineers use a lot, and it deals with approximations as well. Differentials. Recall, the derivative of a function x is written or denoted as dy dx, right? Where y is equal to f of x. dy dx. This is using Leibniz notation, right? But now imagine that the change on your input value is small. And again, small relatively speaking. Meaning 1% of change. Right? compared to your usual input values, 1% of change you allow yourself, either to the right or left. If that is true, mathematicians figure out that then if you are here, right, and you have some base point there, if you allow a very small variation on your input values, relatively speaking, then you can construct this right triangle attached to the tangent line, right? And you can basically approximate this delta y over delta x with the derivative of your function, evaluated at x, right? They are approximately the same. Why? Well, because if you compute the derivative, perhaps you have to consider a variation on x here, a variation on y here. There is a little piece that you're gonna miss, that you're gonna ignore, right? But it's basically the same as considering this delta y, delta x, right? This is the actual output value. This is the one that we get with a linear approximation. They're almost the same. So this assumption, when delta x is small, is a good one, right? They are approximately equal. Now, if we accept that these two are approximately equal to each other, then we can solve for delta y, by multiplying both sides of this equation by delta x. So if we do that, delta x goes multiplying to the right side, right? So we end up with this, delta y equal derivative of f of x times delta x, And we get this interesting formula, right? That is telling me that if somehow I have information about the derivative at some input value x and a small variation on the input values, I can estimate with a high level of accuracy the variation on the output values, right? And you may say, Professor, but why is that a big deal? Well, imagine, right? This function measures your cost function. You're a CEO of a company. This function measures the cost of producing X items. And you want to kind of, in your mind, estimate what will happen if you increase that cost minimally by $1, let's say. What will happen with the output values, right? You know, so increasing by 1 unit, let's say the production, how the cost will change, right? And that should be important to know, right? So if it changes too much, then you shouldn't change your production level, right? But if it doesn't change too much, you couldn't allow yourself to increase your production value, right? Stuff like that. They use this equation a lot in engineering, for example. All right, so mathematicians now, to describe this, then they allow themselves to substitute this delta y for dy, and then they will say dy equal f prime of x times dx. And these guys are called differentials, these two, right? Differentials. So they should differentials. They should be associated with a small amount of change for x and the corresponding change on y, right? Given a small amount of change on the input values. Mathematicians, they call them differentials. They are just this delta y and delta x, right? They just write it like this, kind of to be consistent with this, right? It's kind of, if you consider this to be a fraction, this will go multiplying to the left side, right? Kind of something like that, right? This is not a fraction, it's a derivative, but this kind of comes from here, okay? So when they ask you to compute the differential of a function, basically they want you to take the derivative of the function and multiply it by dx. That's all, okay? This is what we're gonna work on now. So example number 1 says, for each of the following functions, find the differential of y when x is equal to 3 and when the differential of x is 0.1, 0.1. As you can see, guys, this 0.1 relative or compared to 3 is a small, right? It's a small. It's a very small percentage of this number 3, right? That's why they call it small, small. All right, so makes sense to use this formula. All right, so I'm gonna do this with this function and with this function, okay? Solution for A. First, allow me to say, okay, I have a formula dy is f prime of x dx, right? This is the differentials formula. So dy will be equal to what? Derivative of this function. I'm working with part A. The derivative of this function should be just twice x plus 2, right? Plus 2. And then this is just dx, right? So I found a relationship between the differentials of y and differentials of x, right? Now they say use base point 3. So we're gonna substitute this x with 3 and consider that the differential of x is 0.1. So I'm gonna substitute it with 0.1. And then I will be able to compute the differential of y, right? The change of y associated to a small change on x. So put this in your calculator, guys, and that's it. So 2 times 3, which is 6, plus 2. 3 plus 2 times 0.1. That's 0.8, Professor. Yeah, I know. But in case, guys, in your homework, the numbers are not friendly, this is what you gotta do, right? This plus this times this, 0.8. This 0.8 is the variation associated to a small variation of 0.1 on the input values, right? Not much, right? So good. So it means that this function is somehow stable, right? For small changes on x, it corresponds to small changes on y. It's kind of a stable function. So if you can allow a small variation on the input values, not too much is going to happen on the output values, right? Let's see this other case. Yeah, so this was part B, right? Yeah, so this is a new function. So write out your differentials equation, right? dy equal f prime of x times dx. Then dy will be the derivative. The derivative of this cosine function, remember, is minus sign. And then dx here, right? That's it. And then the differential of y will be minus sign of x. But they are telling me that x, the best point, is just 3. It's just 3. Be careful here, guys. This 3 is 3 radians, right? Remember, in calculus, we work in radians. So this guy is 3 radians. Now, the differential is 0.1. So the differential 0.1. So let's find out what is the differential of y when the differential of x is 0.1. Put this in the calculator, and that's all. So if you put this in the calculator, how we do that, Professor? Well, this way. Very important here, guys. Sine of 3, but our decimal calculator by default consider degrees. Change it to radians. Change it to radians as soon as you can. And then 0.1 here, right? 0.1. Negative 0.0141. Okay? 1. Rounded, right? So negative 0.01411. I'm gonna write a note here, a useful note. Make sure your calculator later is set to work in radians. Okay. If you are not using our decimal scientific calculator, you're using other calculator, just make sure that you are working in radians for this computation. All right. Yeah, guys, be careful there. Otherwise, it's gonna give you some other value. All right, great. Example 2, before we go over example 2, I want you to practice in getting these differentials. These differentials, guys, believe it or not, this is gonna serve you in calculus 2, in case you take calculus 2. They're gonna work with these differentials as well. Let's start with this. Can you try this one? It says find, this is straightforward. Yeah, there are a lot of it, so probably I should do this and I should do the next. Yeah, y equals 6x squared minus 6x minus 4. They want you to find this equation, differential of y equal f prime of x differential of x, the relationship between the differentials. Not a problem because I can compute the derivative of this quickly. It's just 2 times 6, 12x minus 6, right? That's goes here for the derivative, right? And dx is just itself dx, right? This is the relationship that they are looking for. So if you look through, no hard to see that this is there, right? For number 9, is there. I think it's just this one. Very good. So as you can see, it's not that difficult. Can you try this one, number 10? Y equal 8x squared minus 2x plus 3. And they want you to figure out the relationship between the differentials. So can you do that? Yeah, very good, very good, very good. Yeah, I have this formula somewhere on your notes. It's a useful formula to deal with differentials. Adriana, Grace, Oscar. Very good, guys, very good. Good work there. It's just this, right? dy, the derivative, which is 16x minus 2 within parentheses, right? dx, this is the relationship between dy and dx. And that, when you look through, the choices is this. Excellent. Now, I'm gonna do this, I'm gonna let you do this, okay? So there's a bunch of them. Yeah, so let's say they give you something with trigonometric functions, a composition of trigonometric function with a quadratic function. Not a problem because, again, dy f prime of x dx, right? So basically, you just have to focus on taking the derivative of this guy, right? It's a composite function, sine function, outside function, a 4x squared inside function. So we're gonna do this. We will say dy, differential of y, derivative, which is gonna be the derivative of our outside function, sine is cosine. Cosine of what? Of the inside function, right? That's what the chain rule says, times the derivative of this inside function, right? But the derivative of this inside function is 2 coming down, multiplying 4 is 8. X stays with 1 less, right? 8x. And then you just attach the dx here, right? Dx. All right? This is the relationship between the differentials of y and the differentials of x. Simplify. Yeah, mathematicians appreciate it when you simplify, and that's it. This is the relationship between the dy and dx. And that, if you look through, is here, right? Here. Very good. Someone wrote something on the chat. Yeah, very good, Sarah. Very good. Yeah, that's what we were headed to. Try to do number 12 now on your own, and then we'll move on. Do this. Function is y equals sine of 2x squared, right? Figure out the relationship between the differentials. Differential of x, differential of y. Yeah, and then we will go ahead with an application. I think it's there, down there. One more. Yeah, and then we'll go over the applications. So when they ask you for this relationship between the differentials, it's not really a big deal. It's just a form that reflects the derivative, right? Yeah. And can be only used when the change on X input values is small. Let me check, Adriana, your answer, number 12. Yeah, very good, Sarah, Adriana, Ruby, CG. Very good, guys. I'm glad that you have picked this up. Yeah, it's not that difficult, right? You start by saying dy equal the derivative. The derivative of this function. Turns out this guy is a composite function. Outside function is sine, inside function 2x squared. So we go ahead and say derivative of the outside function sine is cosine. Cosine, right? Cosine of what? Cosine of the inside function multiplied by the derivative of the inside function, which is 2 coming down multiplied to 4x, right? 4x. This is what it is. And don't forget your dx, the differential of x. Yeah, soon we're going to see applications of this. 4x up front, simple functions up front, complicated ones writing on the right, and then dx. This is it. And for 12, if you look through, this is the guy, right? This is this. Okay, guys, there is one more here, and then we'll go to the application. So try to this one, number 13, so I can show you the applications. Y equal 4 multiplied by cotangent of 1/3 of x cubed, right? They want you to figure out the relationship with the differentials. Y prime, the derivative is gonna get there, right? And then dx. So the derivative goes here, dx. For you to know, as a hint, cotangent should be considered to be your outside function. And this guy is supposed to be your inside function, okay? Inside function. Very good. Yeah, try. Number 4 is not a problem, it's a constant. We're gonna just take this 4 out. Yeah, try it, and then we will talk about the applications for the computation of errors. Derivative of cotangent. Recall, it's on our sheet, right? Recall derivative of cotangent of x with respect to x is equal to minus cosecant square of x, right? Yeah, that one. Yeah, I think it's in one of the sheets. No, this one. This one. No, these are animations. It's there. Derivative of cotangent minus cosecant square, right? Have this sheet somewhere printed out, or if you memorize it, even better, is this. All right, let's do it together. Some students posted answers. Number 13. Yeah, let's yeah, I see here. You guys, I guess, are missing the square. Don't forget the square, right? Yeah, but I think it's close. Let's do it together, right? The derivative. The derivative. Yeah, Sarah. Yeah, Oscar. Very good. Very good. Adriana. Yeah, that's it. Very good. Excellent. Excellent. Very good. Now it's correct, right? Yeah, very good. The derivative of this guy would be right here, dy derivative now. Derivative 4 is a constant, comes outside. The derivative is going to be derivative of cotangent is negative. I'm going to write it within parentheses or perhaps within brackets. Better, cosecant square of something, right? Of this 1/3 x cubed times the derivative of this guy. 3 comes down, multiplies 1/3. 3 times 1, 3, 3 over 3, 1. So this will be as x squared, right? 1x squared. So we write it as x squared, right? The derivative of the inside function. And notice that there is a negative sign there. And then after this comes dx. So dy will be equal to negative 4, let's write this x squared up front, cosecant square of 1/3 of x cubed, right? X cubed. And don't forget the dx, which is this, right? Yeah, excellent. Yeah, the answers are very close to each other, so always be careful. All right, now let's talk about these problems, right? The ones that deal with errors, estimation related to relative errors. So let me explain that to you here on the yeah, there's a couple. And let's finish with this. It's not difficult, you will see. So this says, example 2, the radius of a ball is claimed to be 4.5 inches with a possible error of 0.05 inches. Use differentials to approximate the maximum possible error in calculating the volume of the ball. Between parentheses, the ball has the shape of a sphere. Hint, for the volume of the sphere, use this formula, V equal 4/3 pi r cubed and pi equal 3.14, okay? So let's do this together. All right, first, let's write out the formula, right? The formula for the volume of a sphere, right? The volume of a sphere. We're gonna need that. So we start by saying, okay, volume here is equal to 4/3 pi r cubed, right? R cubed. Next step, we are supposed to go from this equation to the differentials equation, right? So we're gonna do dv dr, but remember the dr goes here, right? So just dv. Yeah, we're used to put it down here, but the dr was over there. dv, here I'm gonna write the derivative. What's the derivative of this? 4/3 pi constant, 3 comes down, r stays with 1 less 2, and then here the dr. So it was supposed to be dv dr, but the dr appears here, right? Yeah, we'll talk about that. Now, this is the relationship between these two differentials, right? Differential of volume, differential of the radius. Now the trick here is this. The differential of the volume, which is gonna be considered the error, the maximum error, right, for the volume of this ball, should be equal to what? These 3's cancel, 4 pi, but they are telling me that pi, they want me to represent or write it as 3.14. Let's follow the instructions, right? This is this. R squared, but what's the R squared? Well, they say that this is the radius 4.5, right? But there is an error on the manufacturing of this radius. That error is 0.05 inches. And is small, the error, compared to the radius, right? Professor, why you say that? Well, relatively speaking, right? This number, 0.05, compared to 4.5 inches is small, right? So it makes sense to use these differentials, right? Yeah, great. Small, so 0.05 goes here. And that's all. Then simply, don't forget the square of this, right? Simply multiply all this in your calculator, and this dV is gonna be the maximum error possible for the manufacturing of this ball, right? Based on the maximum error for the radius, which is this. All right, so putting this in the calculator, follow the instructions, right? If they tell you to use 3.14 for pi, you should do that, right? So 4.5 is squared. And then this times 0.05, gives me 12.717. Let's write it down. 12.717. In the end, as usual, we attach the unit. We are dealing with volume, right? The volume of the sphere. We are measuring the radius in inches. So this should be cubic inches, right? Cubic inches. And this guy, believe it or not, is the following, is the maximum error in the production of these balls, right? For the volume of the ball, right? Of the ball associated to this error, this allowance on the error of the radius, right? That's what this is saying. And you can see that then you can have an idea, right? Look, by changing slightly the radius, look how this changes, right? It's not that small compared to that, right? So it allows you to have an idea, right? A very good idea of what happens with the output value when you change slightly the input value. All right, guys, so go now to the worksheet. Let me show you these exercises. First, let's deal with this, and then we can deal with the volume. Or perhaps since we just did one with the volume, maybe we can use this and then go back there. I'm gonna show you this number 16. I'm gonna ask you to do number 17, okay? Volume equal 4/3 pi r cubed. This is my volume, right? The formula is given there, right? Now, where r is the radius in centimeters, by approximately how much does the volume of a sphere increase when the radius is increased from 3.0 to 3.2, okay? Use 3.14 for pi. Okay, let me go from this relationship between volume and radius to the relationship between differential. Differential of the volume will be derivative, which is gonna be 3 coming down, multiplying this constant, right? 4/3 of pi is just a constant comes out. Derivative of this part, 3 comes down. R squared stays here. That's the derivative. But then remember, you have to write here dr, right? dr. This is the relationship between the differentials. Now, and it makes sense to use this because notice the differential of the radius, right? The radius went from 3 to 3.2. What's that difference? It's 0.2, right? This 0.2 is small compared with the original amount of the radius, 3, right? 3. So that's why it's a good idea to use this. 3 cancels with 3. So I end up with dV equal to 4 pi, but pi, they're saying that I should use 3.14 for pi, right? So that r squared, which r? Well, when you have these two r's, always use the first one, the first r, right? The original value, 3.0 is squared. dr, what is dr? dr is the differential of the radius, right? So what you're gonna do is you're going to subtract last minus first. Maybe we can use colors here. Last minus first, right? Follow, guys? Yeah. So there's gonna be a variation on the radius, right? But you use last 3.2 minus first 3.0. Follow, guys? That is the variation, right? The delta of x, differential of x. And then just compute this. That's all we're gonna do. Compute this. So we go to a calculator. And this is gonna give us, guys, believe it or not, an estimation, a good estimation of how the volume of the sphere is affected by a little change on the value of the radius, right? It turns out, guys, if you're working in production, manufacturing, it turns out that's a good information. Engineers, they use this equation a lot. All right, so I ended up with 22.608. I'm gonna round it to 1 decimal place by looking at the choices, okay? So this should be equal to 22.6 cubic centimeters, right? We're measuring the radius in centimeters or cubic centimeters. And then I look up and it's here, right? Excellent, excellent, right? This is the variation associated to this slight variation on the radius, 0.2, look, not so small. All right, now try this, guys, or to do on your own, right? And then probably if time allows, we will go back to the ones with the area. So try to do this. I will leave this for you to check how we proceeded, right? But basically start with the equation. And most of the time this equation will be given, but just in case it doesn't, write it out somewhere. Yeah, and then take the differentials and you know, this is the original value of the radius. Maybe we should have highlighted this too, right? This comes from there. From there. I see. I see Sarah. For Sarah, yeah, you made my day. You figure this out. Very good, very good. Yeah, it's not that difficult. It's just very computational. So, very good, very good. So, yeah, Oscar also, Grace, very good, guys. Yeah, so we go from this equation to the equation that relates the differential, right? dV. And for that, we need to use the derivative. dV, differential of volume, equal derivative, constant for thirds of pi out, derivative of r cubed, 3 times r squared, and here the r, right? The r. Yeah, and then we do the substitutions, right? We know that this pi, they want us to substitute it with 3.14. Let's follow the instructions. Times 3. By the way, these two guys will cancel, right? R squared. What r? The first one that appears there. There's a variation on the radius, right? It goes from 1.0, the first radius here, squared, times the differential on the radius, right? The difference on these two values. So I'm gonna go this minus this. Yeah, I hope this helps you when you study, guys. Also, it will be it's the last one backwards, right? So be careful that the last one, because the difference turns out to be an operation that's not commutation. 1.1 here, last minus first, 1.0. And that. Now compute this, right, in the calculator, and the answer should be 4 times 3.14. Times 1.0 squared. Professor, that is just 1. I know, guys, but in case this radius is different, this is what you gotta do, right? I'm trying to show you what to do, worst case scenario. Minus 1.0. I get this 1.256, but I'm gonna round it to 1 decimal place by looking at these choices, right? They are all rounded to 1 decimal place. So this rounded should be 1.3, right? 1.3. And in the end, guys, allow yourself to attach the units. We are measuring the radius in centimeters. So this is a volume. So it should come out in cubic centimeters, right? Yeah. Notice, right? This situation is better. Look here, the radius was changed by 0.1 centimeters. And look at the variation on the volume, not much, 1.3. Right? So this is telling you that this situation is more stable than the previous, right? You see, guys? This situation is stable. So you can allow yourself to change the radius, but over here, you gotta be careful because it's not so stable the situation, right? Yeah. Great. Now to finish, guys, maybe if we have time, at least let me show you one of these. This is similar, so let me do this. Same idea here. They give you an area. I think this is much easier. The area in terms of the radius, where r is the radius in centimeters, by approximately how much does the area of the circle decrease? Now decrease, very important here. When the radius is decreased from 2 to 1.9. Use 3.14 for pi. Okay, this is the equation. So differential of area will be derivative multiplied by differential of radius, right? Derivative of this is 2 coming down multiplying pi r differential of radius, right? This is the relationship between the differentials. Now, they say that the radius has changed this way. Initially, it was this, right? Initially, initial value 2 centimeters. A little bit tricky here. 2, 0 initially. But then the variation, remember the variation is always the last value, whatever it is, the last value is this now, right? First, minus the first value, minus this, be careful there, 2.0. This is what you're gonna do, right? So differential on the area should be equal to this. Let's multiply, right? Pi, which they say should be 3.14, right? 3.14, so this pi. They say substitute it for 3.14. Let's follow the instructions, right? So we're gonna do 3.14. The truth is that even if you write pi there, right, in the calculator, it shouldn't change much the answer, right? You should be able to identify your answer, but let's just play safe, 2.0. And then 1.9 minus 2.0. Negative, I get here negative 1.256, right? I am going to round it to 1 decimal place because look at the answers, they are all rounded to 1 decimal place. So that would be negative 1.3, right? Negative 1.3. Yeah, negative 1.3. Let's attach the units. We're dealing with area, measuring the radius in centimeters. So this should come out as a square centimeter, right? Now, negative, professor, when I look through, they're all positive. Well, the wording here says, right? It says here in the question, how much does the area of the circle decreases? It decreases by this amount, right? Area decreases by 1.3 square centimeter, right? This word decreases, the word decreases, guys, substitutes that negative sign. You follow, guys? You can say the change was negative 1.3 square centimeters, right? That's how mathematicians say it. But engineers prefer to say the area decreases by 1.3, right? So therefore, this is the one you have to pick. You follow, guys? Right? Yeah, and this is similar to 14, right? So you shouldn't have a problem with this. Okay, guys. So